Welcome back. So we were talking about how we can study gradient descent and stochastic gradient descent performance on non-convex function, and we argued that smoothness is a condition we need given the fact that we are focusing on the norm of the gradient as our convergence notion. In this video, I want to talk a little bit about another benefit of smoothness, which provides a new perspective for us when we talk about gradient descent. So we talked about gradient descent, I would say, from two perspectives so far. First, we talked about it from the perspective of fixed point calculation, which basically said that finding a stationary point is equivalent to finding fixed points of another function. A natural algorithm is fixed point iteration, which happens to be gradient descent. Okay. We also talked about the fact that gradient descent means that we are locally following the direction of descent. So locally we are minimizing the function, so therefore it is a good idea to explore. Okay. Now here's another perspective, thanks to smoothness. Okay. Which I think is a very nice way for us to think about how to develop better and more general algorithms. Okay. So consider minimizing a function f iteratively, and that's typically what we do. For instance, SGD and gradient descent, right? What we desire is that we always keep making the solution better. What does that mean? If I'm minimizing the function, I want to make sure that the function value at wt plus 1 is always lower than the function value at wt, the current solution. Okay? So this is basically saying that we want our method to satisfy the descent property. Okay? Ideally, we also want to go one step further. So we want to even maximize the progress that we are making. So by that I mean, let's define this function to be the progress function. The amount of progress that I'm going to make if I go from wt, the current solution, to the next solution, wt plus 1. So I want to find the next solution such that this progress is maximized. Okay? So to do this, there is a very nice recipe which is called majorization minimization, when you are minimizing a loss function, or equivalently minorization maximization, when you are maximizing, let's say, profit, utility, or reward. Okay, and the name suggests what the procedure is. So it means that if you are aiming to minimize a function, you iteratively majorize the function, meaning that find an upper bound on the function and minimize that instead. And you keep doing this for a certain number of iterations until convergence. For maximization, instead what you do, you minorize the function. You find the lower bound on the function, and then you maximize that instead. And if you do this iteratively, hopefully you'll find a good solution. So we're going to talk about this procedure a little bit more in more details. And we're going to talk about the connection to gradient descent and see how we can leverage that to, as I mentioned, develop more advanced algorithms. All right. So as I said, we want to maximize the progress, and we will do so through a surrogate upper bound. So this is the majorization step that I talked about. So we assume that we have an upper bound on the function, which has the following properties. The first property is that the upper bound is tight at the current solution. Okay. The second property is that it is an upper bound. Okay, meaning that it is always it always lies above the function value. So, for instance, if this is my function f of w, this is a valid surrogate function. And let's call this wt. Let's call it w star. the minimizer. Okay, so as we can see here, ut is touching the function at wt, so it is tight. It always lies above the function, so it's an upper bound. And the last property is something that we want to be satisfied, is that the bound or the surrogate function is simple to minimize. Okay, because as I mentioned, the procedure is to minimize this surrogate function iteratively. So this is better be simple. Okay, and what will happen, hopefully, is that as you resort to this procedure, you're going to find other upper bounds, such that when you minimize them iteratively, you're going to converge to the minimizer of the original function. Okay, so therefore, what's our majorization minimization procedure? Every time you find the minimizer of the surrogate function, and then you update the surrogate to go from the current surrogate ut to the next surrogate ut plus 1, such that the new surrogate also satisfies these three properties, meaning that it is a valid upper bound, it is tight at the current solution, and also it is simple to minimize. Now, this seems like a mathematical, very mathematical and broad algorithm. And in fact, there are many examples of this algorithm that you may have seen in your other courses. For instance, the K-means algorithm, which is perhaps one of the most famous algorithms when you talk about clustering problems. Unsupervised learning problems where you want to, again, categorize a data into different categories or clusters, and you only have access to basically feature vectors. You don't know the labels. Another instance is the famous expectation maximization algorithm, which is very useful when you want to determine the parameters of mixture models, such as Gaussian mixture models. Now, our goal is to show that gradient descent is also an example of majorization minimization algorithm when the function is smooth. All right. So first, let's talk about why those specific properties. And the idea is that with those properties, we actually have a guarantee on the amount of progress we are making. Essentially, we ensure that we always are making progress. Our algorithm satisfies the descent property. Therefore, it should converge to a nice solution. Okay. So let's see this a little bit more mathematically. So this is the definition of our progress function. It was the progress I was making if I go from the current solution wt to the next solution wt plus 1. Now, using the fact that our surrogate function is basically an upper bound on the function, I can replace this term with this term to find a lower bound on the progress. Again, we want to find the lower bound on the progress to make sure that we are always making progress, right? And that lower bound hopefully is a non-trivial lower bound. So this is why we need the upper bound property. Okay. Now, I claim that we can again lower bound this with this line because wt is the minimizer of ut. Okay. So therefore, wt plus 1 is the minimizer of ut. So by changing wt plus 1 to wt, I again get another lower bound. And finally, I can use the tightness property. This is nothing but ft. So this line is actually an equality, not inequality, but that's okay. Okay, and therefore I'm going to arrive at the function value at wt minus the function value at wt, and that's basically 0. What does this mean? It means that I'm always making progress, right? Why? Because the conclusion is that f of wt is always larger than f of wt plus 1. So I have the descent property. Okay. Now, if we also assume that the loss is bounded from below, which is not a bad assumption, at the end of the day, we are minimizing a function. So if it's not bounded from below, the minimizer is basically, the minimum value is infinity, minus infinity. So if you make this assumption, given that we are always reducing the function value, we're going to converge eventually. Okay? So it will converge or stop at a stationary point eventually. Okay? But this doesn't say how many iterations you have to run your algorithms to find, let's say, an approximate solution. This is called finite time analysis or non-asymptotic analysis. An example of that is basically the theorems we've talked about so far in the course. Okay? All right. Now let's talk about why gradient descent is an example of majorization minimization procedure. Okay? And the idea is that thanks to smoothness, we have a natural upper bound on the function, which happens to be convex quadratic. Therefore, it is easy to minimize. So basically, thanks to smoothness, we can find this nice surrogate function that satisfies all of those three properties that we needed. So we should be able to minimize the function that are smooth quite easily by using majorization minimization. Okay. So again, by smoothness, we have a convex quadratic upper bound on the loss, which we can use it to be our surrogate function. Essentially, our surrogate function is something like this. It's f at wt. So this is basically a constant term. This is a linear term. And this is a convex quadratic term. Okay. So this term is going to look something like that. Now, let's check that this satisfies our properties. First of all, it is tight at wt. Why? Because if I set w to be wt, this term, this term becomes 0. This term also vanishes. So it's easy to say it is tight at wt. It is also always an upper bound on the function because our function is L smooth. And this upper bound is strongly convex. Okay? So it's very easy to optimize. Okay? Now recall our algorithm, our majorization minimization procedure. The idea was that you basically update your solutions by minimizing the surrogate function. Given that my surrogate function is a strongly convex function, all I need to do to find this minimizer is to take the gradient and set it equal to 0. Okay? So essentially I have to do this. If you take the gradient, it's going to be something like this. The constant term, the gradient is 0. The linear term, the gradient is basically the slope. And then finally, the gradient of a quadratic function is going to be something like this. Now, if you do some rearranging, the solution, W, is going to be Wt minus 1 over L times the gradient. And this is something we saw before, right? This is exactly gradient descent with learning rate 1 over L, right? So essentially, the version of gradient descent for which we stated that theorem, okay? More generally, so therefore this result shows that gradient descent with this step size is an instance of the majorization minimization algorithm. And in fact, any gradient descent method with the step size which is smaller than 1 over L is also an instance of majorization minimization, because that will also result in an upper bound on the function. Okay? So essentially, what will happen is that you're going to change this to 1 over 2 eta. So if eta is less than 1 over L, this term will be larger than L over 2. Therefore, it is still a valid upper bound. All right. Now, this is nice because this provides a recipe to design more general algorithms. Okay? So, for instance, one thing we've been avoiding so far in the course is scenarios where we have some constraint in our optimization problem. Okay? And this is very important, especially in deep learning optimization, when not only you care about how your deep learning model performs in terms of, let's say, the training accuracy and test accuracy, but maybe you also have some other criteria in mind. For instance, how robust your method is. Maybe what's the memorization tendency of your model, and things of that nature that we will talk about in this course in future lectures. Okay. To handle it, all we need to do is to again consider the majorization minimization problem, or the majorization minimization perspective to gradient descent, and say that, hey, I had this convex quadratic upper bound that I was minimizing. Now that I have, let's say, some constraint, I perform the minimization over my constraint set. Okay. Now, this update happens to be exactly the update for another method, which is called projected gradient descent, meaning you are still following the direction of descent, but given that the resultant solution may be infeasible, after making the progress, you project back to your constraint set to ensure that the iterate remains feasible. Okay, so these two are essentially identical. Okay, so beyond handling the constraints, sometimes it's useful to use different notions of distance. What do I mean by that? When I look at this upper bound, I have a Euclidean norm square here. Sometimes it is useful to replace this Euclidean norm with another distance or another divergence. Okay, for instance, L1 norm or the KL divergence, things like that that we will talk a little bit more in this course. Okay, so essentially you can consider the following algorithm. Everything is identical to the previous equation except I'm changing the Euclidean distance square to, again, like an abstract notions of divergence, something that captures how similar W and WT are. Okay? A very famous example of this is called mirror descent, and that is very, very useful when W, the parameter that you are optimizing, is a probability vector. Okay? One example of this is in reinforcement learning, where your policy essentially provides the probability of selecting actions. Okay? In that case, when you change the Euclidean norm to something else, you can get much, much faster performance. Because essentially what you're doing, you are exploiting the structure that W is a probability vector and belongs to the probability simplex. And you won't be able to leverage that structure by using the Euclidean norm. Okay. Now, another extensions, again, facilitated by this majorization minimization view, is to replace this gradient with an arbitrary update vector. So all I do, again, same thing, right? So I'm minimizing over like a feasibility set. I have the constant term, this linear term, where now I have replaced the gradient with some update vector G. And then I have the other term, which, again, you think of it as, let's say, Euclidean norm square. Okay. Now, what are examples of this? The examples are, for instance, when I replace the gradient with a stochastic gradient. So an example is a stochastic projected gradient descent. Okay. Or a stochastic version of mirror descent, and things of that nature. Okay? And finally, this also provides a way to again leverage structures and potentially develop better surrogate functions. Okay, so the structure that we talked about here was the smoothness property that enabled us to find this nice convex quadratic upper bound on the function and leverage it here to apply basically majorization minimization. But if the function has other structures, for instance, let's say we know that the second order derivative or the Hessian has some nice properties, we may be able to leverage that to develop better surrogates and therefore develop better optimization algorithms. All right, so therefore we see that the smoothness is nice because, first of all, it provides a way to approach understanding the performance of training algorithms when the function is non-convex, and secondly, it provides a way to to think of gradient descent differently and potentially leverage that to design more advanced algorithms. Now, in the next lecture, we're going to focus on the proof of the theorems we stated for SGD and gradient descent on non-convex but smooth functions. I'll see you next time.